OT is short for operational technology. This is something that is industry specific, so depending on the sector that you're working in, this may or may not apply to you and your work. However, it is something that's very prevalent in manufacturing and industrial operations, and even in the healthcare industry. So we do need to have an awareness of OT. The concept of OT actually predates IT, and historically was mainly mechanical in nature. Just like IT, this evolved over time to include technological advances and digital communication. To outline the main differences in OT and IT, we can think of IT as concerning itself with enterprise systems and networks, where data is processed, it's stored, and it's transported. OT is concerned with physical processes and the machinery that carry out those processes. While there still may be data storage and processing, that doesn't happen at a public internet level as we see with IT. We do see an intersection of OT and IT these days, again due to technological advances, and these operational technology systems are everywhere, again including places like the manufacturing industry, transportation, utilities like water and electricity, the healthcare industry, and more. One of the challenges with OT is that since these systems predate IT concepts, as they continue to implement IT technologies more and more for communication, it makes security a challenge because these systems weren't designed with security in mind. And that's because some of the things that we need to consider for security these days didn't even exist when many of these systems were first realized or built. Having said that, one of the biggest issues with these OT systems is the fact that they often have very outdated digital infrastructure. If you take the United States as an example and look at our common utilities, maybe like power or our water systems, many of these are running legacy softwares and legacy systems that are vulnerable, but which could be extremely costly to update. So this creates the situation that we're currently in, where maybe budgets don't allow for those things to be updated, and where attackers are more and more frequently attempting to target these vulnerable infrastructure systems. In order to better understand OT, let's look at a well-known model called the Purdue model for IT and OT systems. This is used to help us understand how IT and OT systems commonly work together. At the bottom, we have level 0, which are the physical processes. If we take a manufacturing plant as an example, this is where the product is actually being manufactured at level 0 through physical machinery and processes. This machinery may have their own physical sensors to measure things like temperature or pressure as a couple of examples. Next, at level 1, we have intelligent devices. This is where we find devices that have the ability to alter the physical process in some way. Common devices we see here are PLCs, programmable logic controllers, and those are essentially a computer controller used for automating very specific processes. They use sensors to directly interact with the physical processes. At level 2, we have control systems. Something common here is a SCADA. SCADA means supervisory control and data acquisition. This is a system of software and hardware components that allow for real-time data processing and for monitoring of the processes that are happening. Also, we have logging of historical data here. So if we think about the PLCs found at level 1, a control system such as SCADA software can communicate with those PLCs to see metrics and also make any configuration changes as needed through the PLCs. Level 3 is for manufacturing operations systems. This is where we would see systems in place to aggregate all of the production data for monitoring from each individual SCADA, for instance. This allows for systems like MES, manufacturing execution systems, to monitor the overall manufacturing performance. This is also where we would have log gathering in regard to aggregating information for overall performance throughout the business. All of the communication in these lower layers, they happen with dedicated internal networks. All of these previously mentioned layers comprise what we call the manufacturing zone or the OT zone. Next, we have a demilitarized zone or a DMZ in place. This is a recent addition as OT systems have began to integrate with IT systems over recent years. Sometimes we call this layer 3.5 as well. This is where IT and OT systems converge, and we want to have things in place such as domain controllers and firewalls. This is like any typical DMZ that we would think about for a network. Now, the downside here is that many industries converging OT and IT infrastructure have either no DMZ or a DMZ that is severely lacking in security features, which presents a large threat. Next, we move into the enterprise zone or the IT zone. This layer is combined typically within this model into level 4 and 5 for enterprise and business logic systems. This is the typical IT network that we think of today, containing things like data servers, application servers, email systems, and our network infrastructure itself. So with all this in mind, you can see that OT systems now being integrated with IT systems, of course, introduce a larger attack surface, with IT systems being the main entry point for these attacks. For that reason, many of the attack vectors that you think about aren't going to surprise you and will apply to other security areas that we've looked at. Lots of these problems arise from the fact that there simply may not be a budget for these considerations. Manufacturing or maybe public utilities, they often run on notoriously small shoestring type budgets, so that's a big reason why we see vulnerabilities in security. Common goals for OT attacks include our typical goals for any attack that we've looked at before, such as data gathering and reconnaissance, spear phishing, and most commonly, denial of service attacks, especially against critical infrastructure. The main consideration is OT systems which are publicly accessible over the internet. Again, because these were not originally designed with IT infrastructure in mind, they may have weak or even no security protection mechanisms in place in regard to the OT, those same mechanisms that we would think about commonly, such as insecure firewall configurations. There may be misconfigured rules in place, allowing unnecessary access between IT and OT systems, or even the need for legacy protocols, such as Telnet, which we know is a vulnerable protocol. Outdated software is a risk as well, where unpatched or legacy systems may have well-documented vulnerabilities that can allow for OT access. Lack of segmentation in the OT network itself is also a problem. As we've said, these systems were not originally designed with public internet protection in mind. So many OT systems will have a flat, single-layer network architecture where every device may be able to communicate with every other device. Similarly, the IT and OT systems may also operate in the exact same network without a DMZ in place to separate those, as we've previously outlined should be in place in the Purdue model. Our OT hacking methodology is going to consist of the same general steps as our IoT hacking methodology, so these steps will look familiar to you. However, there are some specific dangers and tactics related to OT that we want to discuss here as well. First of all, why would an attacker target OT systems? And the main overarching reason for this is usually to disrupt the processes of the business. We talked about the example of public utilities here in the United States and how those are frequently probed and targeted. In the case of this example, this could be maybe a state-sponsored attack, where disrupting the public utility sector could cause mass chaos or health dangers for a large group of individuals. This could also be more targeted against a specific organization as well. We can break these threats down into some other general categories as well, including the previously mentioned disruption of services through denial of service attacks, or this could be to cause physical damage to the operations of the systems themselves. Many production processes rely on sensitive tools and instrumentation working closely together, so altering the parameters of something like a PLC could cause large losses in the manufacturing process, or even long downtimes. And we also can't forget about the monetary reasons, where an attacker uses maybe ransomware to lock down systems and prevent access, demanding a ransom payment from a company in order to free up their resources. As for the methodology, this of course starts with information gathering. This is specifically performed against ICS, Industrial Control Systems, or SCADA that we've mentioned earlier, Supervisory Control and Data Acquisition Systems. We've looked at Shodan.io, that's a well-known search engine for gathering information from internet-connected devices, and we can search specifically for OT devices with that resource. If we go back out to my web browser, you can see that I am at the Shodan.io search engine, and the most relevant way that we might want to do this when we're information gathering about specific devices is maybe through port numbers. You can see that in the search bar, I've put in port :502. 502 is just one example, and we'll talk about some other common port numbers used by these systems in just a bit. So you can see the search result examples here, and our fourth result you can see is listed as Schneider Electric. This is an ICS device. And in fact, we see the device identification here. If I just copy this device information and I do a quick Google search in a different window for that, you can see that this particular device is in fact a logic controller. It's an Ethernet relay device. So this is obviously connected to the public internet based on our search hit in Shodan. So this is used somewhere to control a manufacturing process. And that's a common way that we might use Shodan against IoT devices when we're gathering information. Of course, as we've looked at, we can narrow this down further by specific geolocations or cities if we're looking for more specific results. There are some well-known ports used by ICS and SCADA that would be of interest to us, in addition to the one that we just looked at, port 502. So let's talk about these. Often these might be unique to a manufacturer of maybe a PLC device or something similar, but there are a handful of popular protocols as well that would be worth exploring, which we'll see commonly used. First, we have something called Modbus over port 502. This is a serial communication protocol used by PLCs, and we just saw an example of that in Shodan. This is typically used to communicate with other PLCs in the same network, and it's also used to interface with a SCADA for controlling these devices. It's estimated that 90% of PLCs deployed in the industry have Modbus communication capabilities, so this is a big one. We also have DNP over port 19999 and DNP3 over port 20000. DNP meaning Distributed Network Protocol. We see these primarily in utilities industries and places like oil and gas industries as well. We have Fieldbus over port range 1089 through 1091. That's used as a way to aggregate communication between multiple sensors or switches and PLC devices. So you can think of this almost like an Ethernet switch, where we're able to distribute connections without having to have direct mesh connections between every single device. We also have EtherCAT over port 34980. That's used for Ethernet-based Fieldbus. And there's Profinet over port range 34962 through 34964. That's an open standard used for industrial Ethernet for exchanging data between controllers and devices. As I said, there are certainly other ports used by ICS and SCADA, which might be manufacturer specific, but I wanted to point out a list of some of the most well-known and widely used that we still see in operation today. These are places we would certainly want to check in our information gathering phase. Our other typical tools will certainly apply here as well, such as Nmap. And in fact, here in my Parrot OS, I'm inside a folder on my drive. You can see this is user, share, Nmap, and inside of the Nmap directory, I'm in the scripts folder. So Nmap does have some built-in scripts, and we've previously looked at using some of these within Nmap. Now this one that I have highlighted here, you can see is called Modbus-Discover. This particular Nmap script is used to discover Modbus device information and to attempt to enumerate that. So if we were going to use that, we could call this up in Nmap, we could point that to this script, and we could point that over port 502, which is the common port used by Modbus. The next phase is vulnerability scanning. We're looking for vulnerabilities in the OT systems themselves and also in the IT devices providing internet connectivity to the OT system. So again, typical tools would apply here like Wireshark. Wireshark can capture packets for those popular ports that we've mentioned that may be used for OT communication. That will allow us to analyze packets to look for vulnerable access points. If we're looking at something like Modbus communication, for example, this is not encrypted communication, so we can easily capture and analyze that data. And also, we can use maybe a specific vulnerability scanning tool like Nessus. They have some really great features dedicated specifically to ICS and SCADA. This is a tool created by Tenable, and it's great for general network vulnerability scanning as well as specific scans such as those against ICS and SCADA. In fact, if we jump over and take a look at their plugins page, they offer a family of plugins not only for SCADA but for a large variety of things. But this particular section is dedicated to SCADA vulnerability discovery. These plugins could be downloaded and installed into the Nessus software for additional vulnerability discovery tactics, in addition to their very robust factory default features. Phase 3 is to launch an attack. There are various tools and methods for this, depending on the communications that are being used. So let's take Modbus as an example again. If we go into my Metasploit console, you can see that I already have that launched here in my Parrot OS, and we search for Modbus, and we hit enter. You can see that we come up with some auxiliary scanners for SCADA, the SCADA category, and specifically for Modbus. So these will specifically detect Modbus master or slave devices. And as we've mentioned, Modbus passes information back and forth. It uses plain text, no authentication, and no encryption. So this would allow us to send in query packets to see their register. And when we say a register, we're talking about the structure inside of a PLC where there's a table containing 16-bit pieces of data, and it's used to control which actions the PLC takes. We also have the ability for Metasploit to alter this register data as well. Another one I'll mention is called Modbus-CLI, and you can see the GitHub repository for that here. If we go back into my Parrot OS terminal, let's exit from my Metasploit console. If we want to install this, because this is not by default installed within Parrot OS, we can say gem install Modbus-CLI, and in my case, you're not going to see any changes take place because I do already have this installed. This program will perform similar actions to what we just looked at with Metasploit, where it's grabbing register or coil values. So if I say Modbus to launch that, that's going to bring up a view of some of our subcommands and sub-arguments that we have available. So we might say something like Modbus read, followed by the IP address that we are targeting. And one more tool I'll mention here is the Industrial Exploitation Framework. Again, you can see the relevant GitHub page here. This is a Python-based tool, and it's similar to Metasploit in that it has built-in attack modules, but these are specifically for scanning and the exploitation of ICS and SCADA devices. Next, we have the Gain Remote Access phase. So here we're obviously trying to take advantage of vulnerabilities and access that we've discovered in order to gain internal access to an OT system. Our Shodan scans, as an example, can be a tremendous resource for finding ways to gain access into these systems, and often these come from the public internet. In the event that we run up against any sort of authentication requirement, one thing we would do is, of course, check for default passwords that might be in place. Here on screen, we have a public GitHub repository called SCADApass. And this is actually a group of researchers that have published a list of default usernames and passwords for SCADA devices. These are sorted by the device type and the vendor names. All of these were obtained freely through vendor documentation, and they've taken the time to compile this and make that publicly available in hopes to bring awareness to the security concerns here. You can see that this can be downloaded as a CSV file, so that's something you might want to reference along with any of your password tools to see if there are weak passwords in place. And finally, we want to maintain the access that we've gained. Typical tactics apply here, such as opening other ports for backdoors into a system, injecting rootkits, or maybe altering firmware, and of course cleaning up our tracks to avoid detection, such as deleting log files. To understand some important countermeasures for OT attacks, let's revisit our Purdue model for IT and OT systems and talk about the considerations at each level. For the physical processes level, physical security is obviously a concern. This is the least common vector in regard to OT attacks, since it does require physical proximity to a device. So our primary concern would be good physical access controls. We want to make sure that manufacturing machinery is in a secure area with physical checks in place to make sure that any unauthorized individuals do not have the ability to gain access. At level 1, we have our PLCs, and at level 2, we have things like SCADA and ICS, which interact with our level 1 devices. Common attacks here would include altering the manufacturing process in some way by maybe altering the way SCADA or ICS interact with PLCs. And we've looked at tools like Metasploit for altering PLC registers themselves as well, which can affect the systems and the processes. Considerations for countermeasures at level 1 and level 2 would include things like using more secure communication protocols. We've mentioned that as an example, Modbus has no security features built in, so we may want to opt for another protocol if possible. We can also use encryption through IPsec to protect this communication as well, even throughout our entire network. At level 3, we have our MES, our Manufacturing Execution System, which aggregates data and controls processes business-wide. Since these systems are often where we see an interface to the public internet in some way, often because they are accessed on devices that have internet connectivity, this is where attacks like ransomware would come into play, or even other types of malware that can allow access to all of the underlying systems in the business. As for protection mechanisms, we would again consider traffic encryption here. We would also want to have these devices protected by things like a local firewall, and we should have an awareness of any unnecessary ports and protocols functioning on a device with MES access. Ideally, we want to access MES from a sandboxed device that is isolated from the rest of the network and even from the public internet if that is feasible for our business purposes. Our DMZ is an important feature as well, and also is susceptible to attempts at denial of service attacks and various types of malware infection. So first and foremost, we want to ensure that we actually have a DMZ in place. We mentioned already that unfortunately, this is missing from the architecture of some OT/IT integration in certain businesses. And of course, we want to ensure that we have configured our DMZ properly for the segregation of the devices and the traffic inside. And finally, at levels 4 and 5, we have our enterprise network and our business logic systems. These are the most publicly available resources in many cases, and they're going to be susceptible to many types of attacks, including but not limited to ransomware, malware, spear phishing, and general network denial of service attacks. We want proper firewalling here, and additionally, next generation security devices like intrusion prevention systems, antivirus, anti-malware solution. All of these are important. We also want to make sure that any unnecessary ports and protocols are closed because we don't want to leave a hole into our network in any way. In addition to the protection mechanisms that we've mentioned, I also want to mention the concept of a honeypot. You may have seen the honeypot tag in one of our Shodan search outputs, where a particular search result was indicated as being a honeypot. A honeypot is essentially a baited trap for attackers. They look like real computer systems, real targets, but they are specifically designed to gain information from a security perspective. By creating a honeypot, we can better understand how attackers may target our networks. They allow a way for us to leave purposefully vulnerable, sandboxed systems online, so that we can log all of the activities that happen against that system as a means of gaining intelligence. This helps us to understand specific areas that we might want to address with our actual enterprise assets. We can certainly build these out from scratch on our own, but there are also specific solutions to create ICS and SCADA honeypot targets. One of those well-known resources is called the HoneyNet Project, which can be found at honeynet.org. They offer open source projects that are very easy to deploy, and they're going to contain common ICS and SCADA protocols that you can use as a honeypot target in order to gain intelligence about how attackers may target your networks in the future.